So in this paper, which has been published in Science Today, we've been testing whether general relativity, this is Einstein's theory of gravity, is the correct theory of gravity on astronomical length scales. So we've known for a long time that on the scale of the solar system, general relativity is either the correct theory of gravity or extremely close to correct. But we don't actually know whether general relativity is the correct description of how gravity works on the scales of individual galaxies or of the universe as a whole. So we used two phenomena. One is called gravitational lensing. So general relativity says that when you have a massive object like a galaxy, that causes space-time to be deformed. And that warping of space-time means that if you have a second galaxy behind it, the light coming from that second galaxy will be deflected. And if the deforming of space-time is enough, you can get multiple images of that background galaxy warped into what we call an Einstein ring. And the radius of that ring, how big that ring is, tells you how much warping of space-time is going on. So we used two telescopes to do this. We took an image of the gravitational lensing using the Hubble Space Telescope, and that let us measure how big the Einstein ring is. And then we used the very large telescope operated by the European Southern Observatory in Chile to measure how fast the stars are moving in the lensing galaxy. So we took spectra. This is measuring how much energy is emitted basically in each color. And those spectra tell us how fast the stars are moving in the galaxy. Measuring how fast the stars are moving tells us how much gravity there must be holding those stars in their orbits. And so comparing the amount of mass that we infer from that with the amount of warping of space-time that we see from the lensing, we're able to test whether the amount of warping is consistent with general relativity. Dark energy is a hypothetical substance that explains why the expansion of the universe is accelerating. So the universe has been expanding ever since the Big Bang, but what's odd, and we've only known this for the last 15 years or so, is that acceleration is getting faster, it's accelerating. Now, naively, you would expect that all of the gravity in the universe, all of the mass, would cause things to pull together and slow down the expansion or have it carry on going at the same rate. You can't really come up easily with a way of explaining why the expansion is getting faster and accelerating. Now, one way of explaining dark energy, one way of getting rid of dark energy entirely, is to say, well, all of that interpretation is based on assuming general relativity is the correct theory of gravity. Now, if it's not, and a lot of theoretical cosmologists have worked on this in the past, you can come up with ways of accelerating the expansion without introducing a dark energy. Now, our work, which we found that general relativity is the correct theory on the scale of individual galaxies, tells us that if you want to explain away dark energy, you have to maintain the validity of general relativity on astronomical length scales.